6-4 Day 2 Exponential Functions. Our objective for today is to find the integral for problems such as this one here. This is a general description of the types of problems that we want to work with, where the integrand is an exponential function with base b raised to the x power. So what integration rule will we have for this? Yesterday we saw the differentiation rule for exponential functions with base b. It is b to the x times the natural log of the base. As we've discussed, for a particular exponential function such as 5 to the x, the base is a constant, in this case 5. So when we apply this differentiation rule, we get 5 to the x times natural log of the base 5. So the natural log of whatever the base is a constant. So why do I want to remind you of this? Because let's think about how we can find an antiderivative for this integral. We're looking for an antiderivative of b to the x. Well, let's try b to the x. Is this correct? If it is correct, when I take the derivative of what I have here, I should get my integrand back. But when I take the derivative of b to the x plus c, the derivative of b to the x is given by our rule from yesterday, so we would get b to the x times natural log of b. The derivative of the constant of integration is 0. So it doesn't give me my integrand back. I have this factor of natural log of b that I don't have in the integrand. But natural log of b for a fixed value of b is a constant. So it's something that I can adjust for very easily. And here's how I'm going to adjust for that in my antiderivative. I'm going to adjust for that by having a constant factor in front of b to the x, so that when I multiply that by natural log of b, I'll get 1. So what should I have? I should have the multiplicative inverse of natural log of b, which is 1 over natural log of b. So if I put that as a constant factor multiplying b to the x, let's see what happens. So now we take our second try, and we're going to see what happens when we differentiate it. If this is the correct antiderivative for b to the x, when I differentiate it, I should get b to the x. So let's see. So I will have the derivative with respect to x of 1 over natural log of b times b to the x plus c. Now, when you take the derivative of plus c, you'll get 0, so you can ignore that, and we'll just focus on what we have here. As we discussed a minute ago, natural log of b for a particular value of b is just a constant. So 1 over natural log of b is just a constant. So to find the derivative here, you're going to use the differentiation rule from yesterday, and you're going to use the constant multiple rule. So the derivative of a constant multiple times a function is the constant multiple times the derivative of the function. And the function we have here is b to the x, and the derivative of that would be, using our rule from yesterday, b to the x times natural log of b. And of course, natural log of b is a constant, so you can cancel the common factor of natural log of b in the numerator and the denominator, leaving you with just b to the x, which is, in fact, the integrand that we started with. So what does that tell us? That tells us that what we have here is the correct antiderivative that we're looking for. So this is what we have for the integral of b to the x dx, the indefinite integral of b to the x dx. Now we'll write the chain rule version of it. If you have b to the u du for the if you have the indefinite integral of b to the u du, you'll just have 1 over natural log of b times b to the u plus c. Now we'll take a look at some examples of applying this integration rule that we just learned. And here's our first example. It's really easy. It fits our integration rule exactly, so we just apply our integration rule exactly. We have the indefinite integral of 3 to the x dx. So here's what we observe. Our base is 3. So according to our integration formula, the antiderivative should be 1 over the natural log of the base, 1 over natural log of 3 times 3 to the x plus our constant of integration. Let's take a look at another simple example. In this one, we also have an indefinite integral that fits our rule exactly. The only difference between 1 and 2 is, in number 1, the base was 3, and in number 2, the base is 9. So let's see how we apply our new integration rule to solve this problem, to find the integral here. So what we have to do is, we look at our integration rule. Whatever the base is, we will have 1 over the natural log of the base in the antiderivative. In our problem, the base is 9, so we have 1 over the natural log of 9. And then we're going to multiply that by b to the x, which is what we have for the integrand. So we multiply that by 9 to the x, and then we have plus c, our constant of integration. Now we look at number 3. In number 3, here's our problem. We have the indefinite integral of cosine x times 5 to the sine x dx. Now, when you look at that, you may not think to use this rule right away, because you don't quite see b to the x quite obviously as we saw in numbers 1 and 2. But what you do see is this. You do see an exponential function with base 5. So you would kind of think, maybe I can use this rule. But you have to make a u-substitution. You have to do a u-substitution. So let's see how that would work. So thinking that we can use our integration rule from today, we're going to try a u-substitution. So our integration rule from today is, if you have the indefinite integral of b to the x dx, or if we use the u-substitution version, b to the u du, then we will have for the antiderivative 1 over natural log of b times b to the u plus c. So what should we let u be? Whatever the function is that we have in the exponent of our power. So the function that we have in the exponent is sine x, so we're going to let u be equal to sine x. But does this work out? Will it work? When we change variables, will we be able to get rid of everything that has x and convert everything to something in terms of u? Basically, will we be able to get this, or a constant multiple of this, after we do our change of variables? So you can see why we should let u be equal to sine x. The next step is to find the differential of u. The differential of u would be, the derivative of sine x is cosine x. So we have du is cosine x times dx. So now we look at this, and we think, okay, here's our u-substitution. Let's see if we can change variables. So how do we change variables? We use our substitution. In place of sine x, we're going to write u. So we have 5 to the u. And in place of cosine x dx, we're going to write du. So we have 5 to the u du. That fits this form exactly, and we're just going to apply it. We're going to apply the integration rule. So what is our integration rule? Our integration rule is this. you look at the base of your power. The base is 5. So our integration rule says the antiderivative is going to be 1 over the natural log of the base. So I have 1 over natural log of 5 times the base to the u power. So I have 5 to the u power plus c. And finally, we need to go back to our original variable. This antiderivative is in terms of u. So now we need to go back to x. So what do we replace u with? U is sine x. So we replace u with sine x. And when we do that, we will get 1 over natural log of 5 times 5 to the sine x plus c. And that is our final answer for number 3. So today we looked at some examples for finding antiderivatives using the integration rule that we learned today.